Our next lesson is called Bivariate Data Analysis. So we're now going to move from one variable statistics into two variable statistics. So statistics contains tools to understand why there is variability in the data set. So remember, variability is how much things are different from each other. Sometimes we try to relate the variability of one variable compared to another when the two variables are linked through a common subject, like person, day, plant, animal. This is called bivariate data analysis. So we're going to look at that in exercise 1. A sample was taken of 10 low and high temperatures for a given day in Fahrenheit in the month of April to try to establish a relationship between a day's low temperature and its high temperature. So you can see the values there. Low temperature is X, high temperature is Y, and the values were recorded. So in part A, it says decide on a scale for both the X and Y axis based on the data set. And it also says consider using axis breaks. So I'm going to highlight that a little bit. And we will include an axis break just to make sure you understand what I mean by that, taking a look at the data. So when you're trying to decide a scale, you want to look at what your lowest X value is, what your highest X value is, and then the same thing for Y. So if I look at my low temperatures, the lowest temp that I have is 26, and the highest temp I have is 45. Whereas in my Y values, my lowest is 50 and my highest is 72. So I highlighted those. I also want to kind of write that in. So this is the lowest X and this is the highest X. And then we also have the lowest Y and the highest Y. That's a good place to start because then you know what you need to make sure you reach. Now, when I look at the lowest, 26, and the lowest of 50, there's a lot of numbers from 0 leading up to that I don't need to look at. So that's why this graph is a great example of one where a break would make sense. So we can kind of jump to what we need and then pick an appropriate scale from there. So here's what I mean. We're going to take a look at this graph, and I'm going to see the low temperature X's are on the X-axis, high temperature on the Y's. Let's talk about low temperatures first. 26 is my lowest one. So if we started somewhere around 20, that would be appropriate. So I'm going to put a break in the graph by drawing these two kind of slanted lines in the first couple blocks, because this technically would start at 0. And we are going to jump up so that this first marking is 20. So we're not going to keep that scale for the rest of the time. That's why you draw a break. I'm jumping up to 20, and now I'm going to pick a consistent scale. I have to get up to 50, so I believe if I go by 2s, I'll be able to do that. So I'll have 2, 4, 6, 8, 10. I'm just going to mark the 10 mark with a 30. Then we can do the same thing. 2, 4, 6, 8, 10 will be 40. 2, 4, 6, 8, 10 will be 50. The highest X value we have is 45, so that's totally fine to get what we need. We'll do the same thing for the Y values. My lowest is actually a 50, so we'll jump right up with the double kind of break like we did before, and we'll let this line be 50. So then we will have the same scale of going by 2s, because that should get me up past 72, which is my highest. So 2, 4, 6, 8, 10, I'll put a 60 here. 2, 4, 6, 8, 10, I'll put a 70 here. 2, 4, 6, 8, 10, 80 will be here. And as you can see, we clearly make the 72 that we need. So this is part of the standard for this, you being able to take a look at the data and pick an appropriate scale, know when to use breaks. And now we'll work from there to start creating our two variable statistics visual, which is going to be a scatter plot. So we will go to part B, create a scatter plot for the data on the grid. And it's called scatter plot because the points are literally scattered. So at this point, we're going to take and plot all of the coordinates onto this XY axis. So why don't you take your time and go ahead and plot all your XY combinations on the graph. And then when you're done, you can double check with my graph to make sure it is correct. So this is approximately what your scatter plot should look like after you plot your XY values. So as I said, it's called a scatter plot because the points are literally scattered. You're not seeing points that fall exactly in a line with a y equals mx plus b exact equation with a constant rate of change. We are going to talk about now, though, how we can draw in what's called a line of best fit that we can write an equation for, find a slope or rate of change, and be able to describe the general trend of the data that we see. So this is your scatter plot. We're now going to move on to do what's called, like I said, the line of best fit. And we'll make a note here that this line should be in the middle of the data. So you're looking at the data and trying to draw a line that you feel would be an appropriate line of best fit towards the middle of the data. So when you draw in this line of best fit, it does not necessarily hit any of the points that you already have graphed. It's more about the location of it, and if it happens to hit some of the points from your scatter plot, that's fine. So we're going to draw in the line of best fit now. I will draw it in, and then you can replicate that in your notes. So here now you can see what I would consider to be the line of best fit. It's in the middle of the data, not necessarily hitting any of the points that we have plotted, but it's representing the general trend of the data that we have in front of us. So in part D, it says calculate the slope of this line you drew by picking off 2 points off of the line, not necessarily data points, as I said, and round your slope to the nearest hundredth if needed. So you can already see here that if we don't all draw the exact same line, our equations or our slopes might be off a little bit from each other. And this is an introduction to the lesson. So as we continue through, introduction to the chapter. So as we continue through, you'll see why there's got to be better ways to do some of this, and we'll talk about how to do that. But for right now, you can kind of follow my line of best fit, seeing it in the middle of the data, and we're going to go ahead and find our slope and round it to the nearest hundredth if needed, okay? So to help us with this, we want to pick 2 points off the line. So I'm going to pick the point 3054, which is right here. And I'll pick the point 4672, which is right here. I can find their exact location. They're falling on a nice grid point. So we'll write those down, 3054, and then also 4672. And we need to calculate the slope for this. So if you recall, slope is the change in y over the change in x, which we can think of as y2 minus y1 over x2 minus x1. That is the slope formula. So I'm going to go back to our original coordinates, and I'm going to label these x1, y1 because they're the x and y from the first coordinate, and x2, y2 because they're the x and y from the second coordinate. Now, a hint I have with calculating slope or rate of change is to create the skeleton outline and then put the numbers in so that if there were any negatives, you don't drop any of the negative symbols. So this would be y2, which is 72, minus y1, which is 54, over x2, which is 46, minus x1, which is 30. And then if we simplify that, we end up with 18 over 16, which they wanted to the nearest hundredth. So when you type it in the calculator, you get a longer, kind of uglier decimal. Well, not ugly, but a longer decimal. And we want to round it to the nearest hundredth, which is 2 decimal places. So that turns out to be approximately 1.13, or for description purposes, it's nice to write that as 1.13 over 1, so we can kind of make sure we hit both of the variables when we describe what the slope means, which is what we're going to do in part E. So it says, how can you interpret the value of the slope in the context of the problem? Use appropriate units. So again, here we're interpreting. That's different than just finding the numbers. And we're interpreting the slope in context of this problem. And that means we have to use appropriate units to be able to describe this appropriately. So I see 1.13, which is a positive, which means that's increasing. It's change in y over change in x. So on the y-axis is the high temperature. On the bottom x is the low temperature. So this is saying there's an increase of 1.13 degrees as the low temperature increases 1 degree. And I'm just describing each of those numbers. So we will write the high temperature increases 1.13 degrees as the low temperature, that's on the bottom, increases 1 degree. So notice my use of the proper units, the correct descriptions of my variables, because then it's in context. And I'm using the word increasing to show that it's positive. Obviously, for decreasing, you want to use that word. So positive means increasing. So then in part F, would you characterize the relationship between the low and high temperature as a positive correlation or a negative correlation? So I kind of want to talk about those two things quickly before we make our decision. Positive correlation, we're talking about everything going up. So that means as x goes up, y also goes up. For negative correlation, we're referring to x going up. As the x increases, the y is coming down. So we have to describe what we think ours is. So when I look at this, I see as x goes up, y also goes up. So this would be positive correlation. So there is a positive correlation because the high and low temperatures are both increasing. So that kind of says, in general, as the low temperature increases, the high temperature also increases. Okay, so now moving on, two variables can have a strong relationship with one another known as a correlation, but might not have a causal relationship. A causal relationship exists when the change in one variable actually causes the change in the other or is one of the primary causes. So in exercise 2, in each of the following scenarios, two variables are given that if plotted would have a strong correlation. A scatter plot where the data falls nearly in a line. So similar to what we saw in our first example. Do two things. One, state whether you think the correlation would be positive or negative. And two, determine if there exists a causal relationship between the two variables. Does one cause the other to happen? So I actually want to give you an opportunity to try these questions without me, A, B, C, and D. And then I'd like you to resume the video to check your answers and go over it with me. Okay, so in part A, the high temperature in New York City and the number of bottles of water sold. So this should be a positive correlation. As the temperature increases, the number of bottles that are sold goes up. In the second part, is it causal or not? It is causal. The hotter it is, the more thirsty people are, and more bottles of water are going to be sold. So make sure you have the correct answer. Please add anything that you're missing from my description. So once again, that would be a positive correlation. As x increases, y also increases. As the temperature goes up, the number of water bottles sold goes up because as it gets hotter, people are more thirsty. That's what's causing it. So this is a causal relationship. In B, a person's height and a person's shoe size. There is a positive correlation. As a person's height increases, their shoe size also increases. This, however, is not a causal relationship. A person's height does not cause their shoe size. It just happens to be that people who are taller tend to have larger feet. So this is not a causal relationship. Make sure you change your answer if you need to. Not causal. Height does not cause the shoe size. In part C, a person's weight and the amount of time spent exercising per week has a negative correlation. The person's weight is going to come down given more exercising time. So as X increases, Y is coming down. This is a causal relationship. The more time you spend exercising leads to greater weight loss and overall lower weight. So this is a causal situation. And then in part D, the number of texts sent per day and the dollar amount of savings for retirement. So this is a negative correlation. The number of texts sent per day goes, as it goes up, the dollar amount of savings for retirement comes down. This is not a causal relationship. The number of texts does not cause the amount of savings. Younger people just tend to send more texts and have less savings because they're younger. They haven't had as much time to save as someone who is older. So it's really, you got to be really careful about correlation versus causation. Correlation is that whole idea of is X increasing, Y increasing, or as X is increasing, is Y decreasing. Causal is the fact that is one causing the other to happen. So you really want to think about that and use these four as your main examples. So then we're going to finish with our very last exercise. It says variables can have extremely strong correlations, but no causal relationship. This is often the case if there is a third variable that causes both, known interestingly as a lurking variable. So in exercise number 3, the table shows the number of firefighters required to fight a given fire versus the dollar damage done to the house by the fire. So you can see that in the XY table. Firefighters here would be X, damage done in dollars would be Y. And the first question we have here is, are the data positively or negatively correlated, and how can you tell? So if I take a look at this, X is going 2, 3, 5, 8, 9. So X is definitely increasing. And then as I look at the damage in dollars, the damage in dollars is also increasing. So Y is also increasing, which means we have a positively correlated relationship. So I would say positively correlated because as the number of firefighters increases, the damage done by fire, by fires in dollars also increases. So in the second question, we're not going to deal with correlated. We already know it's positively correlated. But now we want to think about the causation. Does the number of firefighters cause the damage done to the house? If not, what hidden variable is causing both variables to change? So the number of firefighters is not making the damage to the house worse, right? That does not make sense. One is not causing the other. So the number of firefighters does not cause the damage to the house. So now that we know it doesn't cause it, what is the third variable, the lurking variable that might really be the thing that is affecting or causing this? So when you think about it, if you're sending more firefighters to the actual fire, the reason you're doing that is because you need more manpower. So you need to make sure you have enough people to fight a fire if it's a larger fire. And then if you think of it that way, it's the larger fire or how severe the fire is that's really causing the amount of damage done in dollars to increase. It's not the number of firefighters themselves. You're sending more firefighters because the fire is bigger or severe, so you need more people, and that is what's really affecting the cost. So that's what we're going to write down. The number is determined by the size / severity of the fire. And this affects the cost. So that completes our first lesson in two-variable bivariate data analysis.